The moon is leaving us. Right now, as you sit here, it is drifting away. Slowly, silently, inexorably. Every year, it moves a little farther from Earth, roughly the distance your fingernails grow in a month. It sounds like nothing. But over time, that nothing becomes everything. This is not a guess. This is measured fact. We have known it for decades, confirmed by lasers bouncing off mirrors left on the moon by Apollo astronauts. 50 years of data. 50 years of watching the moon say goodbye. And here is the thing. The moon is not just a rock in the sky. It is our stabilizer, our timekeeper, our silent guardian. It gave us our seasons, our tides, our atmosphere, our very rhythm of life. Without it, Earth would be a very different place. Perhaps unrecognizable. Perhaps lifeless. So why is it leaving? Where did it come from? And what happens when it is finally gone? Tonight, we are going to find out. But before we drift too far, if this journey stirs something in you, if the wonders and mysteries of our cosmos spark wonder inside you, consider subscribing to Calm Cosmic Drift, because this community is built for minds like yours, to wander, to question, and to find a moment of peace in the vastness of it all. And the quietest question of all is this: what is the moon doing right now? It begins with something so small, so impossibly tiny, that you would never notice it in a lifetime. Roughly the length of your thumbnail, about the distance a child's fingernail grows in a month, barely a fraction of the width of a grain of rice when measured against the vast gulf between our world and the one that hangs in our night sky. And yet, this microscopic drift is one of the most profound movements in the solar system. Every year, the moon moves away from Earth. A slow, almost geological creep, a gentle escape that has been underway for billions of years and will continue until the sun itself brings an end to this story. The movement is so gradual that you could watch the moon every night for your entire life and never detect the change. But it is happening. Every moment. Every second. The moon is quietly, patiently, drifting away from us. Think about that for a moment. The moon, our constant companion, the familiar face in the night sky, the subject of poetry and mythology and scientific inquiry for all of human history, is leaving. Not dramatically, not suddenly, but inexorably. Like a friend slowly walking away, glancing back over their shoulder, until one day they are too far to see clearly, and eventually too far to see at all. This is not speculation. This is not hypothesis. This is measured fact, confirmed by half a century of continuous observation. We know the moon is moving away. We know exactly how fast. And we know why. The physics is understood. The forces are mapped. The trajectory is calculated. But knowing the facts is not the same as feeling their weight. To truly understand what the moon's departure means, we must first understand how we came to know it. We must understand the extraordinary effort, the decades of work, the lasers fired across 250,000 miles of space, the mirrors left behind by astronauts that revealed this quiet cosmic truth. So let us begin there. Let us begin with the mirrors. It is July 1969. The world is watching. Neil Armstrong and Buzz Aldrin have just become the first humans to walk on another world. The images are grainy, the audio crackling with static. But the moment is electric. Humanity has reached beyond its home planet for the first time. We have touched another world. Among the scientific experiments the astronauts deploy on the dusty, gray surface of the Sea of Tranquility is a device that seems almost too simple to be revolutionary. A panel of prisms arranged in a square roughly the size of a dinner table. It looks unremarkable, just a flat panel of glass-like material sitting on the lunar surface, reflecting the harsh sunlight. But these are no ordinary prisms. Each one is a corner cube, a geometric shape with one extraordinary property. Any beam of light that enters it is reflected directly back toward its source, regardless of the angle at which it arrives. If you shine a flashlight at it, the light returns to you. If you point a laser at it, the beam comes straight back. The design is elegant, simple, and utterly reliable. No power source is needed. No moving parts. Nothing to break or wear out. Just pure geometry, doing its job for decades, waiting patiently for the lasers to arrive. Apollo 11 left the first of these reflector arrays on the Moon. Apollo 14 and 15 would leave more, each one larger and more capable than the last. The Soviet Union, in its own lunar program, also placed reflectors on the Moon using robotic rovers. Together, these 5 arrays form a network of targets scattered across the lunar surface, each one waiting for a pulse of light from Earth. Half a century later, these mirrors are still there, still working, still reflecting. The astronauts who placed them are gone. The Apollo program is a memory, but the mirrors remain, silent witnesses to humanity's first steps beyond our world. And they continue to serve science in ways their creators could scarcely have imagined. So how do we use them? How do we fire a laser at a target the size of a tabletop from a distance of nearly 400,000 kilometers and expect to hit it? The answer lies in a combination of precision engineering, patient observation, and sheer determination. At observatories in New Mexico, France, Italy, and Germany, powerful telescopes fire laser pulses at the Moon. The beam spreads as it travels across the 250,000 miles of space. By the time it reaches the lunar surface, it has widened to the size of a small city. The mirrors themselves are tiny by comparison. Hitting them with a laser beam that has spread to the width of a city is, as scientists have described it, like using a rifle to hit a moving dime from 2 miles away. But the scientists do not just fire once and hope for the best. They fire repeatedly, thousands of times. The laser pulses are timed with extraordinary precision, aimed at exactly the right coordinates, adjusted for the Moon's motion across the sky. And every so often, the light hits its mark. When it does, a tiny fraction of the light reflects off those Apollo-era mirrors and travels all the way back to Earth. The round trip takes just a few seconds. The light that left the observatory returns to the same telescope, carrying with it information about the Moon's position, its distance, its motion. By measuring the travel time with extraordinary precision, timing the pulse down to the billionth of a second, scientists can calculate the distance to the Moon within an accuracy of roughly the width of a finger, the same amount the Moon moves away each year. The measurement is so precise that it can detect the Moon's wobble, its tidal deformation, even the subtle influence of Earth's rotation on its orbit. This is the Lunar Laser Ranging Experiment, and it has been running continuously for over half a century. The data it has produced is nothing short of revolutionary. It has allowed scientists to measure the Moon's rotation with incredible precision, revealing that the Moon has a liquid core. It has confirmed that ocean tides on Earth have a direct influence on the Moon's orbit. It has provided evidence for Einstein's theory of general relativity. And it has given us the definitive measurement. The Moon is receding at a slow, steady rate. The measurement is precise, consistent across decades of observations. It has become one of the foundational truths of planetary science. But the measurement is only one part of this story. It is the doorway into something far larger. Because once we know the moon is moving away, we have to ask, where did it come from? How close was it before? And what happens when it is gone? These are the questions that lead us deeper into the story of our planet and its companion. A story that begins with a violent collision and ends with a quiet, inevitable farewell. To understand the moon's departure, we must first understand the invisible forces driving it. We must understand gravity and tides and the slow transfer of energy that has been shaping the Earth-Moon system for billions of years. Gravity is the weakest of the fundamental forces, yet it is the one that shapes the universe. It holds planets in orbit around stars, stars in orbit around galaxies, galaxies in vast cosmic webs stretching across billions of light years. It is the force that keeps your feet on the ground and the moon in its orbit. But gravity is not constant. It varies with distance. The closer you are to a massive object, the stronger its gravitational pull. This simple fact is the key to understanding the tides. The moon's gravity does not pull equally on all parts of the Earth. The side of our planet facing the moon feels a stronger gravitational pull than the side facing away. This difference in force stretches the Earth slightly, creating tidal bulges, not just in the oceans, but in the solid rock beneath your feet as well. The Earth is not a perfect sphere. It is slightly elongated, pulled into an egg shape by the moon's gravity. The oceans respond dramatically to this pull, rising and falling in a rhythm that has governed coastal life for billions of years. The ocean tides are the most visible manifestation. Twice a day, water rises and falls along coastlines around the world. This is the moon at work, pulling on our oceans, creating a rhythm that has shaped the evolution of life on Earth. Marine organisms have evolved to synchronize their reproduction with the tides. Coastal ecosystems depend on the ebb and flow of tidal water to cycle nutrients. The entire intertidal zone, one of the most productive habitats on Earth, exists because of the moon's gravitational pull. But there is more. As the Earth rotates, these bulges of water try to keep pointing toward the moon. They want to remain aligned with the moon's gravitational pull. But the Earth spins faster than the moon orbits. Our planet completes a rotation in roughly a single day, while the moon takes about a month to circle us. This mismatch creates friction. The rotating Earth drags the tidal bulges forward, pulling them slightly ahead of the moon's position. Imagine you are holding a bucket of water on a rope and swinging it around your head. The water bulges outward, trying to stay aligned with the force of the spin. Now imagine that the bucket is moving faster than the rope wants it to. The water sloshes forward, constantly trying to catch up. This is what happens with the Earth and the moon. The Earth is spinning faster than the moon's orbit, so the tidal bulges are dragged forward slightly ahead of the moon's position. And here is where the transfer begins. Those tidal bulges, those masses of water that are slightly ahead of the moon, exert their own gravitational pull on the moon. They pull it forward in its orbit, giving it a tiny boost. Think of it like a child on a swing getting an extra push at just the right moment. That forward pull accelerates the moon. It does not speed it up in the sense of going faster around its orbit. Instead, in the strange physics of orbital mechanics, it does something else. When you accelerate an object in orbit, something counterintuitive happens. It does not just speed up, it moves to a higher orbit. Think of it like a weight on the end of a string. If you spin the weight faster, it moves outward. The same thing happens with the moon. As it gets pushed forward in its orbit, it gains energy, and that energy pushes it into a higher, more distant orbit. The result is that the moon drifts outward, slowly, inexorably. This is the same physics that keeps satellites in orbit around Earth. When a satellite fires its thrusters to speed up, it does not just go faster, it moves to a higher orbit. When it fires its thrusters to slow down, it drops to a lower orbit. The moon is constantly, gently, being pushed into a higher orbit by the Earth's tides. And as the moon moves outward, the Earth's rotation slows in response. Not because of some cosmic punishment, but because momentum must be conserved. The angular momentum of the Earth-Moon system is constant. As the moon gains orbital momentum, the Earth loses rotational momentum. The Earth's rotation slows. The days get longer. This has been happening for billions of years, and it will continue until the Earth and Moon become tidally locked. It is a dance of energy and momentum, a gravitational exchange that has been playing out for billions of years. A slow, patient transfer of energy from one celestial body to another. And we can measure it. We can quantify it. We can predict its future. But the story is not as simple as a steady, constant rate. The moon's recession has not always been the same. It has varied over geological time, speeding up and slowing down in response to changes on Earth. Now the picture becomes even more interesting. For most of the time we have studied this phenomenon, the rate of the moon's recession was considered a steady, reliable constant. A simple number, easily understood. But science is never satisfied with simple answers. The deeper we look, the more complexity we find. Geological evidence suggests that the moon's recession has varied significantly over time. Hundreds of millions of years ago, when the continents were arranged differently and the oceans were in different configurations, the rate of recession may have been much faster. During the periods when ice covered much of the planet, the rate of recession actually slowed dramatically. Why would this happen? The answer lies in the configuration of the continents, the shape of the ocean basins, the distribution of land masses, the depth of the seas. All of these factors affect how tidal energy is dissipated. Some ocean basins have exactly the right proportions to create a resonance effect. The water in them sloshes back and forth at a rate close to that of the tides, making the tides larger than they otherwise would be. Think of pushing a child on a swing. If you push at the right moment, the swing goes higher and higher with each push. If you push at the wrong moment, the swing slows down. The same principle applies to the tides. When the natural resonance of an ocean basin matches the tidal rhythm, the tides become amplified. More energy is dissipated. More energy is transferred to the moon. The moon recedes faster. When continental drift changes the shape of ocean basins, the tidal resonance changes too. This means the rate at which the moon recedes can speed up or slow down over geological time. We are currently living in a period when the rate of recession is unusually high. The moon would only have had to recede at its current rate for a fraction of its existence to reach its present position, so the rate must have been much slower at points in the past. The Earth's surface is not static. Continents drift. Ocean basins open and close. Ice ages come and go. All of these changes affect the tides, and all of these changes affect the moon's recession. The moon's orbit is a response not just to the Earth's gravity, but to the entire dynamic system of our planet. But there is another factor at play, one that is deeply connected to our own time, one that we are only beginning to understand. Climate change is warming the oceans. This warming is causing ocean stratification, the layering of water by temperature and salinity, to increase. Warmer water is less dense, so it tends to stay on the surface, creating layers that do not mix easily. This changes how tides propagate through the oceans. It changes the friction, the energy dissipation, the transfer of momentum to the moon. It is also causing sea levels to rise as glaciers and ice sheets melt. Rising sea levels change the shape of coastlines, the depth of the oceans, the configuration of the tidal system. All of these changes affect how ocean tides behave. They alter the amount of tidal friction, the friction that transfers energy from Earth to the moon. The result is that climate change has increased the rate of tidal friction in recent decades. This translates to an additional push to the moon's recession on top of the background trend. It is almost nothing, a tiny, almost imperceptible acceleration. But it is something. And it is a stark reminder that even the grandest celestial processes are connected to what happens on our planet's surface. This discovery bridges astronomy and climate science in a way that would have seemed unlikely just a few decades ago. The moon's orbit, so distant, so seemingly immutable, is responding to the warming of our oceans. We are, in a sense, accelerating the moon's departure from Earth. It is an easy detail to overlook, yet it changes the way we see the universe. Now we must go back, way back to the beginning. To understand where the moon is going, we must first understand where it came from. We must travel billions of years into the past, to a time when the Earth was young, the solar system was chaotic, and the moon did not yet exist. For much of human history, we had no idea how the moon formed. Early astronomers offered guesses. Some thought the moon was a captured asteroid, wandering too close to Earth and falling into orbit. Others believed it formed alongside Earth, like twin siblings born from the same cloud of dust and gas. These were reasonable ideas, but they did not quite fit the evidence. The problem was chemistry. When Apollo astronauts brought back lunar rocks, scientists analyzed them in laboratories on Earth, and they found something puzzling. The moon's composition is remarkably similar to Earth's, almost identical, in fact. The isotopes of oxygen, the ratios of elements, the overall chemical makeup, all of it points to a common origin. This is not what you would expect from a captured asteroid, which would have a completely different chemical signature. It is not what you would expect from a twin sibling either. Twin siblings would have their own distinct histories, their own unique compositions, but the moon and Earth share a chemical fingerprint that suggests something different. There was another clue. The moon has very little iron in its core. Earth, by contrast, has a massive iron core. If they formed together, why would one be so different from the other? If they were captured, why would they share such similar compositions? The evidence was contradictory, confusing, pointing in multiple directions at once. The answers began to emerge decades ago when a group of scientists proposed a radical idea. What if the moon was formed not from a gentle process, but from a catastrophe? What if, early in Earth's history, another planet collided with us? Picture this. It is roughly 4.5 billion years ago. The solar system is young, chaotic, and violent. Planets are still forming from the disk of dust and gas that surrounded the young sun. The inner solar system is crowded with protoplanets, worlds that could have become planets in their own right, but that never quite finished the process. Among them is a Mars-sized body that scientists have named Theia. Theia is on a collision course with Earth. Not a glancing blow, but a direct, catastrophic impact. The two worlds are moving at incredible speeds, their gravitational fields pulling them together. There is no escape. The collision is inevitable. When it strikes, the energy released is almost unimaginable. The impact vaporizes Theia entirely. It melts a large portion of Earth's outer layers. The temperatures reach tens of thousands of degrees, hotter than the surface of the sun. A massive cloud of debris, rock, metal, vaporized silicates, is ejected into orbit around our planet. This debris forms a ring, not unlike the rings of Saturn, but far more massive. It circles the Earth, a disk of molten rock and vaporized metal, glowing with the heat of the impact. And within this ring, gravity begins to work its patient magic. Particles clump together, clumps attract more particles. Over time, perhaps just a few thousand years, these clumps coalesce into a single body. The Moon. This is the giant impact hypothesis, and it has become the leading explanation for how our Moon formed. It explains the chemistry, because the Moon is made from the debris of Earth and Theia combined. It shares Earth's composition because it is literally made from Earth's outer layers, mixed with the vaporized remains of Theia. It explains the lack of iron because the iron from both bodies sank into Earth's core before the debris was ejected. The Moon is made from the lighter, rocky material that remained. It explains the Moon's orbit because the Moon formed from a disk of material orbiting Earth. Its orbit would naturally align with Earth's equator. It explains the Moon's early history, its surface features, its lack of atmosphere. The giant impact hypothesis ties together all of the evidence, providing a coherent picture of the Moon's birth. But the impact did more than just create the Moon. It set the stage for life itself. The giant impact produced a series of effects on Earth that helped prepare it to support life. Let us consider them one by one, because they reveal just how much we owe to that ancient collision. First, the impact dramatically increased Earth's rotation rate. The newly formed Earth spun much faster than any other rocky planet in the solar system. This rapid rotation was crucial because it meant that over billions of years, as the Moon's tidal action slowly slowed the Earth down, the day would gradually lengthen to its current duration. This rate of rotation makes photosynthesis possible and keeps temperatures moderate between freezing and boiling across most of the planet. Compare this to Mercury, where a single day lasts 59 Earth days, resulting in nights so cold and days so hot that life as we know it could never exist. Second, the impact gave Earth its favorable axial tilt. This tilt gives us our seasons, mild enough to support life, but dramatic enough to stimulate evolutionary processes. Without it, there would be no seasonal variations at all, like on Mercury. The seasons drive the cycles of life on Earth, from migration patterns to flowering times to hibernation. They have shaped the evolution of nearly every species on the planet. Third, the glancing collision appears to have stripped away Earth's primordial atmosphere, which was thick with greenhouse gases. Without this removal, Earth might have ended up like Venus, where the atmospheric pressure is immense and surface temperatures are hot enough to melt lead. Instead, the reformed atmosphere, thinner and more balanced, allowed water to condense, oceans to form, and photosynthesis to eventually produce the oxygen we breathe. Fourth, the impactor's iron core fell back to Earth and merged with our own core, enlarging it significantly. This enlargement, combined with Earth's faster rotation, generated a magnetic field far stronger than that of any other rocky planet. This magnetic field deflects the charged particles of the solar wind. Without it, the solar wind would have stripped away much of our atmosphere, just as it did on Mars. Fifth, most of the impactor's mass transferred to Earth, increasing our planet's mass. This increase in mass provided sufficient gravity to keep water vapor from escaping to space before it could condense to form the oceans. Without this extra gravity, Earth might have ended up dry and barren, like the Moon itself. And these were just the immediate effects. After the Moon formed, it continued to give. The Moon's gravitational pull, especially in its early days when it was much closer, generated enormous tides that eroded the land and enriched the oceans with minerals essential for life. The rapid cycling of these tides created tidal pools, ideal environments for concentrating nutrients and possibly even for the origin of life itself. The tidal pools that existed on the early Earth were natural laboratories, places where organic molecules could concentrate, react, and form the first living cells. The Moon's tidal action gradually slowed Earth's rotation from that initial rapid spin. This slowing optimized wind circulation and surface temperatures for the development of life. The slower rotation allowed for more moderate day-night temperature differences, creating a more stable environment for life to evolve. And perhaps most importantly, the Moon stabilized Earth's axial tilt. Without the Moon's gravitational influence, our planet's axis would wobble chaotically, shifting dramatically over millions of years, just like Mars. This stability has been crucial for life. It has allowed for relatively consistent climates over geological timescales. It has given evolution a steady platform on which to build. The Moon has given us so much. It gave us our day, our seasons, our atmosphere, our magnetic field, our oceans, and the stable climate that allowed complex life to evolve. We owe our existence to it, and it is leaving us. There is another gift the Moon gave us, one that is only now coming to light. A gift that protected our atmosphere during Earth's most vulnerable period. A NASA-led study revealed something remarkable. About 4 billion years ago, when the Moon was 3 times closer to Earth than it is today, it had its own magnetic field, and the Earth and Moon's magnetic fields were magnetically connected. The Moon's magnetosphere served as a protective barrier against the harsh solar wind raining down on the early Earth-Moon system. The high-energy solar wind particles could not completely penetrate the coupled magnetic field and strip away the atmosphere. The Moon acted as a shield, deflecting the solar wind, protecting the Earth's fragile atmosphere. This shared magnetic shield persisted for hundreds of millions of years, precisely during the time when life was first emerging on Earth. Without this protection, the solar wind might have stripped away much of our planet's atmosphere. The oxygen you breathe, the nitrogen that fills your lungs, the water that covers our planet, all of it might have been lost. The Moon helped protect our atmosphere when we needed it most. And then, as its interior cooled, it lost its magnetic field. The field diminished significantly and vanished by about 1.5 billion years ago. Without a magnetic field, the solar wind stripped away the Moon's own atmosphere. But by then, Earth's magnetic field had grown strong enough to protect us on its own. The Moon gave us a shield during our most vulnerable period, and then it quietly let go. It is a remarkable story, one that connects the Moon's internal dynamics to the very survival of life on Earth. Now imagine standing on the surface of that early Earth. The sky is not blue. It is likely a hazy orange, thick with volcanic gases. There are no oceans as we know them. The water is still in the atmosphere, yet to condense and fall as rain. The surface is molten, glowing with heat from the impact. It would take hundreds of millions of years for the planet to cool enough for solid rock to form. And above it all, the Moon. It is impossibly close. It orbits at a fraction of its current distance. In the sky, it appears many times larger than it does now. When it rises, it does not just brighten the night, it dominates it. The Moon's gravitational pull on this young Earth is immense. Tides are not gentle lappings of water on a shoreline. They are violent surges, waves that travel thousands of kilometers across a planet-wide ocean, reshaping the surface with every pass. The Moon is so close that it orbits Earth every few hours. A day on this early Earth is just hours long. The planet spins so rapidly that the moon appears to race across the sky, rising and setting multiple times before you could even think to count them. The moon is not just Earth's companion, it is its master. Its gravity is the dominant force shaping the planet's surface, its climate, its very rotation. But even then, the moon is already leaving. The same physics that drives the moon's recession today was at work back then. Tidal friction, the gravitational tug-of-war between Earth and moon, was far more powerful. The moon receded much more rapidly in those early days. The rate was not the slow creep we measure today. It was likely meters per year, or even more. Each year, the moon moved significantly farther away. Each century, it lost tens of meters. Each millennium, kilometers. Over hundreds of millions of years, the moon gradually spiraled outward. Its orbital period lengthened. Earth's rotation slowed. The days grew longer. Tidal waves subsided. The surface cooled. Life began to emerge. And as the moon drifted farther away, its influence on Earth became more subtle, more gentle. It no longer controlled the planet with brute force. Instead, it began to play a different role. It became the stabilizer. What would Earth be like if the moon had never existed? It is a question that reveals just how deeply the moon has shaped our world. A thought experiment that illuminates the moon's profound influence on our planet. Without the moon, Earth's rotation would be faster. Days would be dramatically shorter, perhaps as short as 6 hours. The winds would be more violent, the weather more extreme. The rapid rotation would generate powerful atmospheric currents, creating storms far more intense than anything we experience today. Without the moon's tidal forces, the early oceans might have been relatively stagnant. The mixing of nutrients that tides provide might never have occurred. The tidal pools that may have been the birthplace of life would not exist. The intertidal zones that are some of the most productive habitats on Earth would be absent. Life might have taken a different path. It might never have emerged from the oceans at all. Or if it did, it might not have diversified in the way it did. The evolutionary pressures that drove life from the oceans to the land might have been absent. The entire history of life on Earth might have been different. Without the moon, there would be no solar eclipses, no lunar eclipses, no tides to mark the rhythms of life, no gentle light to guide nocturnal animals, no cultural symbol that has inspired poets and artists for millennia. The night sky would be darker, the moonless nights deeper, the stars brighter. And without the moon, there would be no stable seasons. Earth's axis would wobble chaotically, shifting dramatically over tens of thousands of years. Climate shifts would be extreme and unpredictable. Ice ages would come and go without pattern. The tropics would freeze while the poles melted. Life would face a far more hostile and unstable environment. The moon has shaped not just our planet, but our species. Its cycles are embedded in our calendars, our mythologies, our very sense of time. The word month comes from moon. Our ancestors watched its phases and built the first calendars around them. The moon has been a constant companion through all of human history, a familiar face in the night sky, a reminder that we are not alone on this world, and it is leaving us. There is a moment in the story of the moon that is perhaps more poignant than any other. Today, we are lucky. Incredibly, improbably lucky. The moon and the sun appear almost exactly the same size in our sky. This is a cosmic coincidence. The sun is much larger than the moon, but it is also much farther away. The result is a perfect balance. When the moon passes between Earth and the sun, it can block the sun's disk entirely, creating a total solar eclipse. For a few precious minutes, day turns to night. The stars emerge, the temperature drops, birds stop singing, animals become confused, and the sun's corona, its ghostly outer atmosphere, becomes visible, a silver halo surrounding the black disk of the moon. It is one of the most breathtaking sights in nature, a moment of perfect alignment, of cosmic geometry, of beauty and wonder. People travel across the world to witness total solar eclipses. They describe the experience as transcendent, spiritual, life-changing. The corona glowing in the darkness, the sudden quiet, the strange twilight. And it is temporary. As the moon continues its slow recession, its apparent size in the sky will gradually shrink. One day, long after our species has either vanished or evolved into something unrecognizable, the moon will no longer be large enough to cover the sun completely. Instead of total eclipses, we will have annular eclipses. The moon will pass in front of the sun, but a ring of sunlight will remain visible around its edges. It will be beautiful in its own way, but it will not be the same. Eventually, even annular eclipses will become rare. The moon will be so far away that it will no longer block the sun's light at all. It will simply drift across the sky, a tiny speck passing in front of a star, barely noticeable to any observer who might be watching. The great eclipses of the past will be a memory. The corona will no longer be visible. The strange twilight will no longer fall. We are living in the brief window of cosmic history when total solar eclipses are possible. It is a fleeting moment, a narrow slice of time in the life of our planet, and we are here to witness it. That changes the way we see the universe. But the loss of eclipses is just the beginning. As the moon moves farther away, its gravitational influence on Earth weakens. It has been our planet's stabilizer for billions of years, keeping our axis tilted at a steady angle. Without that stability, things begin to change. The Earth's axis will slowly become less predictable. It will wobble, shifting dramatically over millions of years. The climate will respond to these shifts. Ice ages will become more extreme. The seasons will grow more chaotic. In some eras, the poles will receive direct sunlight, melting ice caps and flooding coastlines. In others, the equator will freeze. The stable conditions that have allowed complex life to flourish will become a thing of the past. This is not a sudden catastrophe. It will happen over geological timescales, hundreds of millions of years, but it will happen. Life will adapt, as it always has. Species will migrate. Evolution will take new paths. Some forms of life may thrive in the new conditions, others may not. The history of life on Earth is a history of change, and this will be just another chapter. But there is a deeper question, a question that goes beyond climate and biology. What is the moon doing really? The moon is stealing time from us, not in a metaphorical sense, literally. As the moon moves farther away, Earth's rotation slows. The days grow longer. This has been happening for billions of years. When the moon was born, a day lasted just hours. The days lengthened over time, to 10 hours, to 12, to 20. Today, a day lasts 24 hours. In the distant future, a day will last longer. Think about that. The length of a day is not fixed. It is changing, slowly but surely, because of the moon. Every generation lives on a planet that rotates just a little bit slower than the one before. The time you have is being stretched, millimeter by millimeter, over geological time. Eventually, if the moon continues its retreat long enough, Earth's rotation will slow to match the moon's orbital period. One side of Earth will permanently face the moon. The moon will no longer rise and set. It will hang fixed in the sky, visible only from one half of the planet. This is called tidal locking, and it has already happened to the moon. That is why we always see the same face, the same sea of craters and dark plains, when we look up at night. Earth will become tidally locked to the moon. But here is the twist. This will not happen in our solar system's future. There is not enough time. The sun is a star. Like all stars, it has a finite lifetime. Right now, it is in the middle of its existence, steadily burning hydrogen in its core. But eventually the hydrogen will run out. The sun will begin to expand. This will happen in billions of years. The sun will become a red giant. Its outer layers will swell, engulfing Mercury, then Venus, then Earth. Our planet will be consumed. The oceans will boil away. The atmosphere will be stripped. The surface will melt. And then the Earth itself will be vaporized, its atoms scattered into space. The moon, if it still exists by then, will not survive. It will be pulled into the expanding sun, or it will be flung into the dark void of interstellar space. The story of Earth and Moon, which began in violence and continued through billions of years of quiet companionship, will end. But here is the extraordinary part. Earth will become tidally locked to the moon before the sun engulfs it. The moon will stop moving away. It will hang motionless in the sky, a permanent fixture on one side of the planet. This will happen billions of years from now. But the sun will destroy Earth far sooner. The tidal locking will never happen. The moon will continue its slow retreat until the sun itself brings an end to the story. It is an easy detail to overlook, yet it changes the way we see the universe. We have been talking about billions of years, numbers so large they are almost impossible to grasp. Let us bring it back to something human. The moon is leaving us at the speed your fingernails grow. It is so slow that you will never see it. Your children will never see it. Your grandchildren will never see it. 100 generations from now, the moon will be measurably farther away, but no one will notice. And yet, this slow, silent departure is one of the most profound truths about our place in the cosmos. It is a reminder that nothing is permanent. Not the moon, not the Earth, not the sun, not even the stars. Everything changes. Everything drifts. Everything, eventually, moves on. There is a quiet beauty in this. We are living in a moment of transition. We are the generation that exists between the moon's violent birth and its quiet farewell. We look up at the same moon that our ancestors looked at. We see the same craters, the same dark plains, the same gentle glow. But we know something they did not. We know that this is temporary. We know that one day the moon will no longer be our companion. That does not make it sad. It makes it sacred. Let us pause for a moment and reflect on what the moon has given us. The moon gave us our day, a cycle of light and darkness that governs our sleep, our work, our very biology. It gave us our seasons, the predictable rhythm of spring, summer, autumn, and winter that has guided agriculture and civilization for millennia. It gave us our tides, the ebb and flow of oceans that has shaped coastlines guided navigation, and influenced the evolution of marine life. It gave us our atmosphere by shielding it from the solar wind during Earth's most vulnerable period. It gave us our magnetic field by enlarging Earth's core and increasing our planet's mass. The Moon gave us the stability to evolve from single-celled organisms to complex, intelligent beings. It gave us a constant companion in the night sky. It gave us poetry and art and mythology. It gave us eclipses that remind us of our smallness and our wonder. It gave us a destination, the only other world human beings have ever set foot upon. And now, it is giving us something else, a lesson in impermanence. The Moon has shaped us. It has shaped our biology, our culture, our sense of time. It has given us eclipses and tides, and poetry and wonder. It has been a constant presence in the night sky, a familiar face in a changing world, and it is leaving us. But perhaps that is the point. Perhaps the meaning of the Moon is not in its permanence, but in its impermanence. Perhaps we are meant to appreciate it precisely because it will not last forever. Stand outside tonight if you can. Look up. Find the Moon. It might be a thin crescent, a half disk, a full circle of silver. Watch it for a moment. Think about how far away it is. Think about how fast it is moving. Think about the fact that every second it is drifting farther from us. And then think about this. You are alive at a time when total solar eclipses are possible. You are alive at a time when the Moon still stabilizes our planet. You are alive at a time when the Moon is still close enough to touch our imagination. You are the lucky generation. Not because you are special, but because you are here. Because you exist at this precise moment in cosmic history when the Moon is still close enough to move us, to inspire us, to remind us of our place in the universe. The Moon is leaving us. But for now, it is still here. And that is everything. And so, we come to the end of our journey. We have traveled from the Moon's birth in a cloud of vaporized rock, through billions of years of slow companionship, to the distant future when it will finally drift away. We have seen that the Moon is not just a rock in the sky. It is a stabilizer, a thief of time, a cosmic coincidence, a reminder of the impermanence of all things. And we have seen that we are the lucky ones. We are alive in the narrow window of cosmic history, when the Moon still hangs large in our sky, still offers its light and its gravity and its silent companionship. The Moon is leaving us, but it has not left yet. And so, the next time you look up at the night sky, pause for just a moment. Let your mind drift. Think about the distance, the time, the slow, gentle pull of invisible forces. Think about the story that brought us here, and the story that lies ahead. The Moon is leaving, but we are still here, and that is enough. The deeper we look, the stranger it becomes. But perhaps the deeper we look, the more we understand, and perhaps that understanding is the greatest gift of all.